Yeah, so today we are very welcome to have Jian Kang from ShanghaiTech to talk about the continuum theory for twisted bilayer graphene. And Jian encouraged us to ask questions. Jian, please share your screen.
Okay, let me see. Can you see my PowerPoint?
I can see your slides.
Okay.
I can see the PowerPoint. Yes. Yeah.
Okay. Give me a second. Okay. Okay. Okay, great. So first of all, I would like to thank Jian Wang to give me such a wonderful chance to present our recent work. So the title of my today's talk is Continuum Field Theory for the twisted bilayer graphene. My name is Jian Kang from ShanghaiTech University. And my today's talk is completely based on these two works recently posted to arXiv and submitted to PRB. Okay, so first I would like to introduce my collaborators, Professor Oscar Buffett from Florida State University, also affiliated with the National Magnetic Field Lab. And this is the outline of my talk. So first I will give a very brief, very quick introduction on twisted bilayer graphene. I guess most of the stuff you have already obtained from by reading papers. And then, in the second part, I will discuss the physics of this so-called BM model. I will basically talk about the band properties as well as why this BM model, should be improved if you want to have some quantitative comparison with the experiments. And in the last part, I will basically introduce our constructed continuum model with this arbitrary lattice deformation. Okay, so first let me talk about the history of this twisted bilayer graphene. So as most of you have already known, this system goes back to like 2017. The end of 2017 or the early of 2018. So when Professor Pablo in MIT basically found the phase diagrams of this system. So first, when the twisted angle of this system is tuned to be very close to the magic one, it's basically very close to 1.1 degrees. And if you start to dope the systems, and you find out that when the thinning is very close to +2 or -2, the system actually goes into this so-called correlated insulating phase, and also close to this insulating phases, Professor Pablo also found out that there are also two superconductivity phase near this insulating phase. So if you only look at this phase diagram, you realize this is very similar to the phase diagrams of the couplings, and that's pretty much why this insulating phases back to that time was identified as a multi-insulating phase. But very soon, people start to realize that this system actually is unique. It's not that similar to the couplings. For example, if you look at a different thinning, that is a thinning of 3, and also, if you align this sample, this twisted bilayer graphene with the so-called hexagon boron nitride substrate. If the system is in alignment with the substrate, and people start to realize that this system actually is in the quantum Hall phase when u = 3. So first, this was noticed by Professor David Gordon at Stanford University, and when he measured this RXY, he found some non-zero value. Of course, if you look at the plots, this sigma xy is not quantized. But very soon, it was realized by Andrew Young that in his lab that this system actually is in the quantum Hall phase, and the sigma xy actually is quantized, and u = 3 if the sample is aligned with with HBN substrate. And gradually, people start to realize that the system, I mean, this insulating phases and nu equal to +2 or -2 is not quite unique. For example, I mean, the Creighton from the Columbia University and Andrew Young from UCSB, I mean, they published this this measurement of the resistivity for the same system, and he noted that even if the sample is misaligned, even if the sample misaligned with the substrate, and people still found a new phase, a new insulating phase at nu equal to 3. Now, this phase is different from Continuum score because sigma xy is the measure sigma xy is 0. Okay, so it's more like a trivial insulating phase. And also, Professor Efthoff, back to that time when he stayed in SFO, he identified almost like at every integer fitting, he identified the so-called correlating insulating phases and also the superconductivity phases, not just appeared close to ± -2, but also appears almost everywhere. Now, of course, I mean, at the same time, the theories also try to understand what is the mechanism, what is the properties of this insulating phases, and also this superconductivity phases. So on the left side of this PowerPoint, at least, I mean, here is of course a very limited number of papers. At least here also include the papers by me and by Vafak. We basically try to understand what is the properties of these insulating phases. And here, I mean, basically there are some papers discussing the properties of superconductivity. Okay, so so this is basically the experiment of the twisted bilayer graphene. So here I will give so in next I will give a very quick discussion, a quick introduction on the system itself. So twisted bilayer graphene, I mean, by its name, it's really just bilayer graphene. So I mean, that means if you look at this system in the real system, it's still two-dimensional. But what's different from the graphene? It's the size of this superlattice. So if the twist angle is commensurate and the translation symmetry can be partially restored, so that the system we can identify what is the superlattice structure of this system. So it's still triangular, but the number of atoms, the number of carbon atoms in each unit cell, that is really huge. For example, when the twist angle is near the magic one, we see that each unit cell contains more than 10,000 different carbon atoms. And also, if you look at the stacking pattern in the real space, it's basically contained almost everything. It contains AA, AB, and BA, all these different stacking patterns in the real space. And also, if you look at the energies, just look at the energy scales of this system. If you only focus on the narrow bandwidth, first you look at what is the bandwidth of the narrow bands. It's about like 10 MeV, depending on which model you use. And also, if you look at the interaction energy scales, basically that's Coulomb interactions, and it gives you about 20 MeV. Okay, so that's basically the energy scales of associated with the narrow bands in these systems. And also, if you only want to understand the physics very close to the charge neutrality point, or in another way, I mean, the so-called low energy electrons. So first, so here, if you look at the plot, this red and this blue hexagon, they are basically the Brilliant zone of the monolayer graphene on the top and the bottom layers. And you can see that they're twisted relative to each other. Basically, that corresponds to the twist angle. So if you only look at the low energy physics, your low energy electrons. So basically that means you only look at the electrons very close to the corner of this red and the blue hexagons. Okay. So first thing you want to ask, what is a folded Brilliant zone? What is the Brilliant zone of the twisted bilayer graphene? I mean, that's simple. You connect those two corners together, and then you draw a hexagon. So this blue hexagon, that's basically the hexagon. I mean, that's basically the brilliant zone of the twisted bilayer graphene. And if you look at the size of this hexagon, I mean, this folded hexagon, I mean, that's simple. That's just twisted angle times the size of the monolayer hexagon. I mean, the brilliant zone of the monolayer graphene. So firstly, I mean, if just for theoretical, completely for theoretical purpose, if we can turn off the interlayer tunnelings, I mean, the low energy physics are basically described by the Dirac cones of each monolayer graphene. That's basically I mean, the Dirac cone located at these corners of this two hexagons, okay, blue and red. And if you, I mean, we can also try to estimate what is the bandwidth of these bands near the charge neutrality point. They're basically the Fermi velocity of the Dirac cone times k theta. Well, k theta is basically the size of this folded hexagon. Okay, now we turn on the interlayer tunneling. Clearly, I mean, at the intersection points, I mean, those bands will start to split it, and the gap between those two bands are basically determined by the magnitude of the interlayer tunnelings. So clearly, I mean, if the interlayer tunneling, let's say, and also the original bandwidth can be tuned together, so we can see that, I mean, this this reconstructed bands are actually can be greatly shrinked. I mean, the bandwidth can be greatly shrinked, and eventually we can get bands near the charge neutrality that has very small bandwidth. Okay, so that basically is a very simple picture of why this why we can have this narrow bands near the charge neutrality point. Okay, so after having this very simple, I mean, very intuitive picture of the narrow bands, we may want to ask, I mean, how to describe, I mean, how to obtain, quantitatively obtain the bandwidth, the dispersion of the bands near the charge neutrality point. So if you look at the history, I mean, usually there are two different approaches. One approach, that is, we directly start from the microscopic model. So here, I mean, basically is we start from the microscopic time binding models. So here, I mean, this T is so-called hopping function, and this is C and C dagger. They're just annihilated and created fermion operators. So basically, this J, they represent the level, the top, and the bottom. The S is sublattice, and the RS, that's basically the position, the position of the carbon atoms. So in our paper, or in this talk, I will basically discuss two different microscopic models. The first one, of course, I mean, is given by Mu and Koshilo in this 2012 PRB papers. I mean, basically, I mean, one important simplification or one important properties of this hopping function is that, I mean, this hopping actually, if you look at the hopping functions, it's basically in plane isotropic. So basically, it does not depend on the direction of the hopping. Okay, so this one was basically given by Mu and Koshilo based on the stated cost method. Another one is basically given by Fang and Professor Kaxiras in this 2016 PRB papers. And so an important difference is that in this hopping in this model, first of all, the hopping looks more complicated, but also more importantly, I mean, if you look at the interlayer hopping, actually this depends on the direction of the hopping. So it's not isotropic anymore. Actually, it's the interlayer hopping actually is anisotropic. Now, of course, I mean, in principle, you can use this microscopic time binding model, try to discuss physics, and even, let's say, try to figure out what is strongly correlated in insulated states. But the problem of this approach is that it's too complicated. Why? Because as I said, I mean, at the magic angle, each unit cell contains more than 10,000 different common atoms. That is, even for this time binding model, even if you just want to get what is the band dispersion, what is the band structure, the matrix, the size of the matrix actually is about 10,000 times 10,000. So that's too complicated to do any calculations, even to do some quantitative calculations. That's already too complicated. So instead, that means people have to find out some alternative, some simplification for this microscopic models. So nowadays, if you look at pretty much almost all the theoretical calculations, it always starts from something called BM model. So it was first proposed by Bistritzer-MacDonald in this 2011 PNAS papers. So if you look at the format of this BM model, it looks quite complicated. It looks quite simple. So if you look at the diagonal part, the diagonal part is simple. Is basically sigma times p. That's basically the dispersion or the model for the Dirac of the monolayer graphene. And off diagonal, you have this TR that's given by this form. So this TR basically represents so-called interlayer tunnelings. It contains just two different parameters, W0 and W1. So in total, this BM model really just have three different parameters. You have VF, you have Fermi velocity of the monolayer graphene, monolayer Dirac. So if you look at the energy scale of this term, that's about 200 MeV, 0.2 electron volt. And also you have this W0 and W1. They basically present so-called interlayer intra-sublattice and inter-sublattice tunnelings. And if you look at the energy scale of those two parameters, they're about the same. Basically, it's 100 MeV. So this interlayer tunneling and this intralayer dispersion, that's basically have the same energy scale. And also, if you look at this TR, you have this E minus IQJR. That's basically represents the momentum transfer between the interlayer and the intralayer, between the top and the bottom layers. And this TR, it contains only three different momentum: Q1, Q2, Q3. Okay, so that's basically three smallest possible momentum transfers. Okay. So in principle, you can also contain other momentum transfers, but all the other momentums are actually larger. If you look at the magnitude, they are larger than Q1, Q2, Q3. Okay. And here I basically plot the band dispersions near the charge neutrality point. So first, I mean, there is one interesting limit discovered by Grisha and Ashwin. So in this 2018 PIL papers, that is, if you set this W0, if you set this interlayer but intra-sublattice tunneling to 0, and this W1 that's close to 0.583, the whole system actually goes into this exactly flat band limit. So you can see that at this limit, the bands near the charge neutrality point are actually exactly flat. And it has some really nice properties. It even allows you to figure out what is the exact strongly correlated states at each integer fillings. Okay. Of course, I mean, this is more like a theoretical limit, but more relevant, if you look at the experiments, you look at the real materials, more relevant, I mean, that is, well, this ratio, I mean, that is about 0.8. Okay, and also if you look at the remote bands, the so-called remote bands, and for most of the parameter regions, I mean, that the remote bands and the lateral bands, they have some band gap, but this band gap close when the ratio between W0 and W1 is larger than 0.9. So larger than 0.9, the band gap actually vanishes. Okay, we can also look at some topological properties of this associated with this lateral bands. So here, I mean, I basically plot this Wilson loop this two bands near the chiral point. So as you can see, like no matter how I change this ratio, this W0 to W1 starting from 0 to 0.85. So remember that band gap start to close at 0.9. So this is pretty much, so this is like the upper limit of this ratio when the band gap is still open. But no matter what, no matter how I change, how I vary this ratio, you can see that these two Wilson loops always cross with each other at 0.5. Okay, so that's basically shows the two bands actually associated with at the chiral point, they're actually topological. Okay. So now, I mean, let's revisit this BM model. Let's see why. I mean, let's see what is. I mean, do we have some shortcomings of this BM model? So one thing we noted that if you look at all this derivation, okay, it's not just limited to BM model. Actually, is pretty much almost all the continuum model. They're always written in the momentum space. And if you look at the derivation, or the sum, they're always based on the assumption of periodicity. Okay, so that means that in principle, this derivation of the continuum field theory, or I mean, this continuum model does not allow the appearance of these aperiodic terms, such as disorder, such as like lattice deformation, etc. Okay, so you always assume. You always construct it based on the assumption of the periodicity. So that basically means it does not allow us try to understand the physics of the disorders. And also, if you go back to the BM model, at least in the first version, I mean, it's derived only for the rigid twist. It does not assume the existence of any lattice relaxation. However, we know that in the real systems, this lattice relaxation always exists, no matter what. Okay, so that means at least the first version of this BM model may not be quite faithfully reflect the true physics of this twisted bilayer graphene. And also interesting, if you look at this TR. This TR, maybe that is this interlayer tunneling terms. As I already said, it contains only 3 different momentum transfer: Q1, Q2, and Q3. Okay, they are the 3 smallest possible momentum transfers. And why should we include only 3 of them? Why not just more? I mean, of course, I mean, this actually is based on the decay properties of this Fourier transformation of this interlayer tunnelings. So if I look at the Fourier transformation of this interlayer tunneling, so basically you can see that it decays as the momentum increases. So if you look at Q1, Q2, and Q3, they correspond here. Okay, and here you can see that even if you can read the numbers, you can see that this VQ, that is about 110 MeV. That's exactly the value of W0 and W1. And now if you go to the second shell of the possible momentum transfer, and you can see that they are already becomes very, very small. I mean, if you look at the numerical values of this second shell, is about like 1.5 MeV. So that's already very small compared with the first shell. So that's why we are allowed to neglect the momentum transfer with the large moment. That's why we are allowed to neglect the other momentum transfers. Okay, so this is what happened for the rigid twist. Now, as I said, in principle, I mean, if you look at all the realistic terms, all the realistic systems, and the system always have this lattice relaxation. Now you immediately realize that other terms have to be added to the BM model to reflect the physics of this lattice relaxation. Now, based on the previous experience, based on the, I mean, people have already done quite a lot for the monolayer graphene. So that is when the lattice, when you have some local distortion or local deformation of the of the monomer graphenes, one big thing you have to consider is this so-called pseudo-vector field. Okay, so if you do the calculation for the twisted bilayer graphene, you realize that this pseudo-vector field terms actually introduce energy scales of 50 to 100 MeV, depending. The exact number, of course, depends on the relaxation model, depends on the elastic models you choose, but no matter which model you choose, is always the energy scale of this term is always 50 to like 100 MeV. And of course, the way to add this pseudo-vector field is simple. You simply, if you look at this diagonal part, you simply replace P by P plus A, where A is just the pseudo-vector field. Okay, and also now you look at the TR. As I said, TR contains two different parameters, W0 and W1. Without lattice relaxation, you can derive, you can prove that these two values must be the same. Okay, W0 and W1 must be the same. But once you introduce lattice relaxation, you notice that the AA region actually is shrinked, but the AB or BA region actually is expanded. Now let's go back to the form of TR. That means that immediately tells you that the W0 and it should be smaller than W1 if you look at the relaxation. Okay, because W0 that's intra-sublattice relaxation tunneling. That's basically AA or BB, and W1 that's actually inter-sublattice tunneling. That's AB or BA corresponds to. But also, there is another question to ask. If we have lattice relaxation, should we also change the form of TR? So one thing you can notice that maybe this lattice relaxation actually will introduce the terms with larger momentum transfer. So it's not just limited to Q1, Q2, Q3, three different momentum transfers. Maybe we have to include large. We have to include more terms with large momentum transfer. And actually, as we see that this is true. And such terms are actually not small. Okay. So the last thing to question the BM model is the BM model. In principle, if you look at the BM model, in the diagonal part, you only have like a sigma dot P, so it's only linear terms. And the TR, if you look at TR, you look at all this W0, W1 is independent of the momentum. So basically, this represents the lowest order terms in the gradient expansion. Now the question is, should we also include all the higher order terms? For example, like P square terms in the interlayer part, and also this gradient tunneling in the interlayer part. And even without doing any calculation, you can try to estimate the magnitude of these terms, and it turns out all these terms are about like 5 MeV. So this is really a small number initially if you look at this. However, what I want to say here is that these numbers are actually not that small. If you have some terms with 5 MeV, first you notice that it's already comparable with the bandwidth at the magic angle. Okay, so it's comparable to the kinetic terms you put in the Hamiltonian. Now, even if you go to the strong coupling limit, even if you claim that the kinetic terms or other terms are basically behaves like a perturbation, it's still important. Why? Because and also ZTL has already done this DMRG calculation, we noted that the manifold of the ground states are actually not unique. Okay, it contains many different candidate states that strongly compete with each other. For example, if you look at this DMRG calculations, you look at this basically is for nu equal to 3, and the semi-metal and the conomermous Hall and also this C2T stripe phase, all these phases actually have very close energies. Okay, you can see the energy difference actually, let's say, is It's basically 0.2 or 0.3 MeV. So that means if you really want to compare with the experiments, these 5 MeV terms should not be neglected. It should really be put into your Hamiltonian. And only after that, you are able to calculate, or you are able to select the correct ground state and compare with the experiments. Okay. So this basically means, so yeah. Yes.
Yeah. I have a simple question regarding the previous slides. So maybe you can finish this slides and I can ask my question.
You want me to finish this slide?
If you want, but maybe I can just.
Well, you can just ask me a question now.
So
yeah, it doesn't matter.
I have a question about the pseudo-magnetic field. Is that the strain effect? Can you clarify a little bit? Is this a strain effect or not? Yeah.
Yeah. Okay. So because even if you do not apply any external strain, because the lattice has to relax with each self. I mean, for example, I mean, you can imagine that the angle with the AA configuration actually is higher than the angle of associated with AB or BA configuration. So that means the lattice actually, even without any external strain, the lattice will form some local strain, and this local strain actually can be reflected by this pseudo-vector field.
So usually people say this AA region shrinking effect is captured by W0 and W1. Here you point out there is an additional effect from the A.
Exactly.
And in a continuous theory, will you also take into account strain effect?
Yes. You mean to apply the external strain or internal?
Yeah, the graphene level.
In principle, you can apply external strain with our formula. Okay, so let me just mention a little bit about our continuum field theory. So our continuum field theory was based on the assumption that the lattice deformation is smooth. That's pretty much the only assumption. Okay, so that means you can apply some external strain, and you can still use our formula to obtain the continuum field theory, the continuum model. That's what I mean. Okay. So basically, yeah. So basically, our approach is quite universal. That's what. But in this talk, I will not talk about that. I will only talk about. I will only focus on the zero strain case.
Okay. Yeah. Thank you.
Okay, you're welcome. So basically, what I want to say here is that I hope that you are persuaded that although this BM model is really powerful, is really, I mean, they really grasp some essential physics, but to quantitatively compare with the experiments, to quantitatively select the correct ground state, this BM model needs to be improved from at least this aspects. Okay, so now the question is, I mean, it can be improved from, I mean, with so many factors. So the question is, do we have some systematic way to derive the continuum model directly from the microscopic model? So basically, this is what I want to present. Okay, so first, I mean, I will say several things about the properties of our continuum field theory. So first, I would say this field theory actually is written in the real space. So that means, in principle, I mean, we do not assume anything like periodicities. So in principle, we can also use this continuum field theory to understand the disorder, or this physics, or this local physics. We start from the microscopic time-binding model. So we have already, I have already introduced this formula here. So basically, this J is top or bottom nail. This S is sublattice. This RS is the position of the carbon atoms, and this T is hopping functions. Now, one interesting, you noted that I use two different position vectors. One is this RS, another one is X. So which one? I mean, what's the difference between those two? So what's the difference is that this X actually is a real position. Okay, so this X is a real position. This small r is the original position of the carbon atoms. So that is the position before any deformation, before any twist or strain or anything. Okay, so that means the relation between X and R is described by this formula. And all this, if you look at this U perp, that's basically in plane deformation, and this perp is the deformation along the z direction. So that is a deformation out of plane. And this U basically include twist, include strain, and this disorder, all this stuff. Now, our field theory, as I already mentioned, is based on the assumption that this U, both U parallel and U perp, so both U's are smooth, but we do not assume U is small. Okay, as long as U is smooth, that's fine. Okay, and also because this C, this Fermi operator, they are local, and we want to write this one in terms of the field operators. So this equation basically, this formula basically tells us how to transform between C and psi, where psi is the field operators. Okay, where R is continuous, and this is C basically it's a Fermi operator as a position R. Okay, and in principle, this C contains two different parts, both value k and value minus k. But here in the rest of my talk, I will basically focus on this value k. Okay, so that is the first part. So once you figure out all this, and you just substitute this part into this time-binding model and try to write in the continuum space. And but before that, I want to say several things. So first, what I should emphasize here is that the field operator, although here it's written in terms of R, but eventually we will change to the coordinate of X, not R. The reason actually is simple. If you want to use R, okay, remember that we do assume U is smooth, but U is not small. So that means when U is large, you may introduce, if you still want to use R as coordinates, you may start to introduce some non-local couplings between top and bottom layers. So that is really bad for field theory. Okay, so that's why we should choose X, the real positions after deformation. Okay, so that is X, not R. So this difference actually is so those two different approaches that actually is called the Lagrangian versus unarial formulations. And also in some contexts, it's also, I mean, when people also call this as crystal or lab frame. So if you want to use R, so that is means you work in the crystal frame. Otherwise, if you use X, that means you use you work in the lab frame. Okay. Okay, and also this plot basically reflects what is the difference between X and R. So R is really like the position of the carbon atoms before deformation, as this left plot shows. And after you do some twist, after you do some local twist or local relaxation or even corrugations, then this carbon atoms has been moved from position R to position X. Okay, so basically this plot basically, or this schematic describes the difference between R and X. And now let me just present our so-called master formula. So I will just skip all these derivations and just give you this master formula. So it looks so initially this one looks complicated, and in some sense, yes, it is complicated. And but several things you noted that it contains. Okay. So first thing, if you look at the formula, you notice that we have this J terms. This J base is really just Jacobian determinant. That was introduced because you want to change from R, from R coordinates to the X coordinates. So I mean, after you do this transformation, you start to introduce this Jacobi determinant, and also this field operators. If you want to keep this anti-commutation invariant, you also need to introduce some Jacobi determinant. Okay, this T basically is the hopping functions. Okay, after this, if you do some gradient expansion, and you introduce some variables X and Y, so after gradient expansion, this go back to our maybe to the formula maybe we're more familiar with. For example, if you look at this side against side, that's clearly just the context couplings. And also this one, if you look at the second terms in this bracket, that's basically the first order derivative couplings in the expansion. Okay. So basically, this is our master formula. So you may want to question that what is the effect? How about this master formula looks really complicated than BM model. So you want to look at what is the physics of each terms in this BM model. So first, let's look at this interlayer dispersion. Okay, so this is interlayer dispersion. So this one, when this J and J prime, they're the same. So initially you realize that this contains lots of terms. The first term is simple, it's just chemical potential. The second term, you can see that is a sigma dot P plus A terms. I mean, that's basically it's this A field, as I already mentioned, comes from the pseudo-vector field. That arises because we also include lattice deformation here. This sigma dot P, that's basically Dirac dispersion terms. And as I said, this pseudo-vector field, if you look at the energy scales in the real systems, that's about 50 to 100 MeV in TBG when the twist angle is magic. And I should also mention that this P plus A terms, although it shows as gauging invariant terms in the linear order in the first order derivative, but if you go to the second order derivative, this gauging invariance actually loops. Okay, it keeps only at the first order terms. So all other terms, and also all other terms, they are actually like P square terms. Okay, that's second order derivative terms. And you look at the energy scale, that's 5 MeV. But the reason why we should keep these terms is because it's really comparable to the bandwidth. Okay, that's why we want to keep all these terms. So that's for the intralayer dispersion. Now for the interlayer tunnelings, we write the interlayer tunnelings as two different parts. One is this T, this TSS prime X. That's basically this so-called contact couplings. Okay, so if you look at the largest term of this contact couplings, that's about 100 MeV. Okay, that's basically consistent with BM model when W0 and W1 is also 100 MeV. Now the second terms, we write this as anti-commutation between P and this lambda. Okay, so these terms clearly, is proportional to the momentum, and it's called gradient couplings. And you look at the leading, the largest terms of this gradient couplings, that's about 5 MeV. Okay, so you can see that is almost like one order smaller, well, more than one order smaller than the contact terms. Okay. However, if we look at the BM model, this T term, they basically contains W0 and W1. Okay. However, after careful calculations, we realized that this T terms, this contact couplings, also contains another terms, so-called I sigma 3. Okay. So initially, this W0 and W1, if you look at the expression of TR in the BM model, as you can see that it contains only sigma 0, sigma 1, and sigma 2. But now, I mean, we realize that it should also contains I sigma 3. And this I sigma 3, first, I mean, is allowed by all the symmetries in the BM model, like C2T symmetries. I mean, it's allowed. However, I mean, in our calculation, this I sigma 3 actually strongly breaks this particle hole symmetries. Okay, this particle symmetry could be strongly broken by I sigma 3. Of course, this particle hole symmetry could also be broken by this gradient couplings, but it's like the next order. Okay, the dominant part is still by this I sigma 3 terms. And also, I mean, we found out that when the lattice relaxation exists, I mean, we have this Tx and this lambda x, they have to include the contributions from large momentum transfer. So that means it's not just limited to this three black arrows, that is Q1, Q2, Q3, the 3 smallest momentum transfer, but now, I mean, it has to also include the contribution from second shell, from the third shell, or even the fourth shells. Okay, and all these terms, all the appearance of all these large momentum transfer terms, they are actually induced by the lattice relaxation. Okay, now if you look at the magnitude of this larger momentum transfer terms, it could be as large as 20 MeV. So that means it's not negligible at all. It has to be included once you want to include lattice relaxation. Okay, if you don't want to include lattice relaxation, that's fine. I mean, you don't have this large momentum transfer terms. But once you want to include them, you have to include this large momentum transfer. Okay, they're not negligible. That's what I mean. Now we can also compare the band dispersion from this continuum model to the time binding models. And as you can see that when this twisted angle is near the magical one, you can see that the microscopic model and the continuum model, they agree really well. The top one, if you look at the left column, the top one is without relaxation, and the bottom one is with relaxation. And you can see this band gap actually opens because of the relaxation. Otherwise, you don't have any the band gap actually close. Okay, so the left part is for Cauchy's model, and the right part is for Professor Kaxira's model. Okay, you can. I mean, one interesting thing is if you look at what happened at Charlie trap point, you see that those two dispersions, when the lattice relaxation is included, those two dispersions are actually close. They're not that different. Okay, so now you may want to say, okay, whether these two models give some similar continuum model or is different. To answer these questions, I mean, we can compare what is the properties of the Hilbert space near the for the bands near the charging trap point. So one thing we can do is we can look at the sublattice polarization. So this one, the left one, is the sublattice polarization of the for the Cauchy's model. You can say that the polarization actually varies between 0.6 and 0.85. However, if you look at the sublattice polarization for Kaxira's model, that actually varies from 0.3 to 0.7. So it's very different. Like minimum, if you look at most regions of this burning zone, I mean, for Cauchy, most of them is 0.6, but for Kaxira's model, most of them is 0.3. So they're very different. Although the dispersion looks similar, but the Hilbert space, I mean, for us, I mean, more important thing is Hilbert space. They're quite different. Okay, we can also look at the particle symmetry. Okay, so first we can look at how about the dispersion. Well, the dispersion already breaks particle symmetry a lot. So as you can see that the dispersion, okay, actually is already quite particle symmetric. for the dispersion. You can also ask what happened for the wave function. What happened for the Hilbert space? Is the Hilbert space near the charging neutrality point? Are they still like a particle symmetric or not? Okay, and so here we basically shows shows the number W1, which describes the particle asymmetry near the charging neutrality point. So if this W1 is 1, so that means the Hilbert space is exactly particle symmetric. If it's smaller than 1, it actually is different by 1 by quite a lot. That means the Hilbert space is particle asymmetric. So for Continuous model, you can say that the Hilbert space, if you look at the number 1, is very, very close to 1. So that means for this, for Continuous model, even the dispersion breaks particle symmetry quite a lot. But if you look at the Hilbert space, is still very particle symmetric. So that means if you look at the interactions, if you are familiar with the story of twisted bilayer graphene, so that means if you look at the interaction is still SO4 symmetric. Now, however, if you look at the continuous model, okay, so near the gamma point, you can see that this number 1 is like a 0.8, okay, or 0.85. That means it already start to break particle significantly. So that means the interaction for this model, significantly deviates from the SO4 symmetry. And one interesting question to ask is, what is a ground state? Is a ground state at charge, let's say a charge neutrality point for this model is still MAC state, or is something different? That could be some interesting theoretical questions to ask or try to answer. Okay, we can also look at other properties of the Hilbert space. So, for example, here is a Wilson loop. So, for left one, that's Continuous model, and for the right one, it's Cox-Series model. So that means compared with the Continuous model, Cox-Series model actually deviates even more from the chiral limit. Okay, so and these properties of the Wilson loop or the distribution of the barrier curvature, that's very important to understand the insulating phases at nu equal to 3. So that means those two models may give you different state, different ground state at nu equal to 3. Okay, and also, and the lastly, I want to basically discuss a little bit interesting about the chiral limit. So remember that in Grisha's and Ashwin's PIL, this chiral limit is discussed without any lattice relaxation. That means when this pseudo-vector field A is set to be 0, so if you go back to BM model, you can have this chiral limit. So what happened if you add this pseudo-vector field? Okay, so what we found out here is that even if you add this pseudo-vector field, okay, you can still have this exactly flat band limit as shown here. So the only difference, if you compare with the BM model, the only difference is that the change of this ratio, W1 divided by VFK theta, or in a different way, that is, what is the magic angle when this exactly flat band limit occurs? So we found out that if you add this A field, you can still have this exactly flat band limit, but the magic angle actually got decreased. Okay, so starting from like 1.07 degree, decreased to 0.8 degrees roughly. Okay, so that means that the addition of this vector field is not, does not really kill this exact flat limit. It just shifts the magic angle to some smaller value. Okay, so we also noted that this This model is also discussed even later in this paper by Ledwith, Ashwin, and Daniel Parker. Okay. So, so finally, this is the conclusion slide. So basically, I hope I do some job to basically present our systematic method to derive this continuum theory. And also, I hope you are also persuaded to really match the dispersion. I mean, the BM model is not enough. You have to include many other different terms, and also we also discussed we also try to generalize this kind of limit. I mean, when this A field, when this pseudo-vector field is added. And this is the end of my talk. And thank you for your attention.
Mm-hmm. Yeah, thank you a lot. So I have a couple of questions. First, in the one slide back, you have this this slides. So the pseudo-magnetic field has opposite sign of the two layers. Is that correct?
Yeah, because here, I mean, the reason is simple because the distortion of these two layers are actually opposite in sign. Okay, we try to do the so-called heterostrain or whatever. Okay. I mean, if you have yeah, so this if the strain has the same sign, that basically means you are talking about like a homostrain or something like that. Okay. So that means that means for the top. So if you don't have any external strain, okay, if you just let the lattice to deform itself. So if you look at U parallel top and U parallel bottom, they have opposite sign, exactly opposite sign. So that's why this A field, A field has opposite sign.
Okay, so the A field can be explicitly written down as a function of the displacement of the function U, right?
Yeah, exactly. That's basically the first order derivative.
Okay. Yeah. Another question is, you mentioned in the interlayer tunneling term, there's additionally new sigma 3 particle Hall symmetry breaking term. So what is the sign of the particle symmetry breaking determined, or is a tuning degraph then?
Interesting question. I think this sign has some gauge freedom.
So if you look at the band structure, band structure, maybe one slide after, here. So the first band structure is particle Hall symmetric. So in the remaining three, you have a curve particle symmetry breaking. So the trend, whether you break in this way or break in that way, is determined on.
Interesting question. Because so this is different. So this is for Cauchon's model. In Cauchon's model, this I sigma 3 actually is tiny. You can almost neglect this I sigma. Oh, so I didn't mention this. So the appearance of this I sigma 3 seems to be related with with whether this this interlayer tunneling is isotropic or anisotropic. Because in Cauchon's model, if you look at interlayer tunneling, it's isotropic. And in this model, the I sigma 3 is almost zero, I mean, almost negligible. And it shows, I mean, for Caxiros model, because it's anisotropic interlayer tunneling, and the I sigma 3, if you look at this term, the magnitude is about 5 MeV. Okay, so I sigma 3 only shows for Caxiros model, which basically is plotted at the right column. Now you ask what is the sign? I mean, the sign of I sigma 3. That's an interesting question. I haven't thought about this. Now we calculate this is positive sign, but Wait, let me think. Wait. I think this asymmetry is really no. I mean, okay. It's possibly. I guess it's possibly just a gauge choice. I think it's really just gauge choice. When it matters is really just magnitude. It's not the sign.
Okay. I see. Oscar also has a comment about this sign. Okay. Yeah, maybe not important. Yeah.
The sign of the I sigma 3 is the same as if you just took a BM model but rotated the Pauli matrices in the diagonal part, and then you gauged it away so that there's no rotation in the two Pauli matrices. Then it will show up on the off-diagonal term as I sigma 3. The one that Jian is describing adds to that.
Okay.
And that comes from, as Jian stressed, from the anisotropic tunneling between the two layers, which is threefold symmetry, but not azimuthally symmetry fully.
So it's basically a gauge choice.
Well, it's just as much of a gauge choice as if you just took a BM model and you had theta over 2 and minus theta over 2 on the other side, on the other two layers. But the important point is that it adds to that term. So there's a little bit of a particle hole asymmetry in the BM model as written when you include the rotation of the Pauli matrices.
Right.
Okay, so now you could now transform just the BM model in such a way that the Pauli matrices on the block diagonal terms in the Hamiltonian do not contain that rotation. So in the chiral limit, if you do that, as you know very well, then this disappears completely. But if you're away from the chiral limit, it doesn't disappear. Some of this will show up on the interlayer tunneling part as I sigma 3.
Okay.
So the term that Jian is describing adds to that. It doesn't subtract from it. It doesn't make it smaller. It makes it bigger.
Okay. I see. Okay. Thank you for clarification.
Sure, you're welcome.
Maybe our last question is, usually in the continuum theory for solid states, lattice defect is an interesting thing to consider. For example, the dislocation can be described by torsion, and the disclination density is described by curvature. Is that your next step to consider? Like, for example, to describe the magic angle disorders or dislocations?
In principle, you can apply this continuum field theory to study that. I mean, this continuum field theory, I think, is really provide a tool to study this effect.
Okay. Do we have other questions from audience? So if no, let's thank Jian again. Thank you for this very wonderful talk. Okay, thank you. See you next time.
See you. Bye.
Bye.